marvelous. It did smell at my house, and my dog was like, "What is this smell?" So we'll do an acid-base indicated lab shortly, and after that, we should be able to knock out the rest of the, not the rest notes, but a couple of balance chemical equations that relate to this unit. And then after that, we have a couple of problems to solve. So we really are like, the majority of the notes have been taken. So keep looking over those, specifically the definitions. They are definitely the hardest, I think, to remember. But my group was here Friday. How do you remember Arrhenius? It's talking about some Arrhenius definitions. Oh yeah, agua, right? So Arrhenius is how does the substance act in water? Well, Arrhenius in water don't really work, but Arrhenius in agua. Okay, Bronsted-Lowry acids and bases are dependent upon what action? Giving and receiving what? Protons, right? Hydrogen ions. So I
Miss Enlow, I need Elliot Trumboy to come to the office with his keys.
Hey, thanks. Okay, so acid.
Thank you.
Thank you. So the Arrhenius acids and bases are talking how they behave in water. The Bronsted-Lowry acids and bases are talking about their ability to gain or accept a proton, which is just an H+. And I said, how do you remember the Bronsted acids?
Bad.
They're bad acids. Okay, BAD means Bronsted acids are donors. BAD, Bronsted acids are donors. And the other one's BABA, BBA. Bronsted bases are acceptors. And then of what?
Proton.
A proton. Okay, so then the Lewis acids and bases category relates to their ability to accept or donate electron pairs, right? And that relates back to our Lewis dot diagrams, electron pairs we drew all the time. So those three big definitions are what we're going to be referencing quite a bit, but the Bronsted probably the one that's most prevalent. Okay, 6 strong acids. Only tell me one. Tell me one. Do you have your notes? You weren't here. Sorry, Avery, tell me one acid. Hydrochloric acid. Morgan, tell me another. Nitric acid. James, tell me another. Tell me that formula. H2SO4. Niall, tell me another.
Hydrobromic acid.
Hydrobromic, HBr. Scott, tell me another.
Sulfuric acid.
Got it already.
Perchloric acid.
Perchloric. Give me that formula.
HCl.
HCl4. What's the last binary one? Hydroiodic. Okay, so there's 3 binary and 3 ternary. Those are your 6 strong acids. If you're not in the 6 strong acid group, what are you? No. Okay, very well, you could be a base. You very well could. But if you're not, if you're an acid and you're not in the 6 strong, you're weak acid. Okay. And weak acids, what's the definition of weak?
Not strong.
Give me what it means in like advanced terminology. Don't just go counter.
Ionize completely.
Doesn't ionize completely. Right. Doesn't ionize, doesn't dissociate 100%. Strong ones, they never actually exist like this unless they're in their solid form. They actually ionize and break apart. You get people who were not here Friday specifically need to be listening and stop talking to their neighbors. Thank you very much. If you're a weak acid, then you predominantly look like this. You don't have your H+ and your counter ion as ionized as the other ones do. Strong bases, they look like a B, like this on the periodic table. Give me where it starts. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, is that here? Nope, calcium hydroxide, ooh, a little higher here, okay. Calcium hydroxide, strontium hydroxide, and barium hydroxide. All of these are hydroxides, right? And that's how they're strong bases. Which ones are dibasic, meaning they have 2 hydroxides? The second group, because that's group 2A, and they have the 2+ charge, so they have to have 2 OHs, the hydroxides, to count to balance their charges. Okay, give me a property, Abby, of an acid. Some of these are going to be common sense. Lemon juice is sour. Right, okay. So counter that. So acids are sour. Bases are bitter. Who's ever had soap in their mouth for saying not so great words? Okay, it gets all up in your teeth. Like she puts the soap bar in there. Mom, good old mom. Okay. So yep, we've all tasted bitter soap. What's another property of an acid, Allie? Look at your stuff.
They burn.
They burn. Okay, so we've all had a cut before. We've cut a lemon. It's like, it's burning. It's just kind of tingles. So we know that they're sour. They burn like an open cut. Do they react with metals, yay or nay? Yes, and when they react with metals, what do they produce? They do a single replacement and they make hydrogen gas. Okay. So the MX is the metal salt, basically, and they make hydrogen gas. That's how we definitely can see it reacting. It's making a gas. And there was one more thing you guys were saying. Conductive in aqueous solution, right? Generally, they're conductive because they're very strong electrolytes. The strong ones aren't even. All right, so speaking of being conductive, which of these do you think would make more ions to be more conductive? Scott. Because it's strong acid. What's the name of this acid? Don't you say hydro, people. It is ternary.
Acetic acid.
So acetic acid, right? Because this is acetate, C2H3O2, and you change the acetate ending to ic acid. Do not say hydro. Hydro means what? Binary. Hydro does not mean hydrogen. Okay, every acid's got a hydrogen. We don't want to say it. We say acid again, that means it's an acid. Bronsted bases, give me an example of something that could act as a Bronsted base. We know they're BA, right? We know that they're hydrogen ion acceptors. Who can accept an H+? Say again?
Someone in the secretary?
Well, so Bronsted bases don't necessarily have to be a hydroxide. Like all those strong bases we were talking about, the B, those are Arrhenius bases because their definition is Arrhenius bases make what in water? What do Arrhenius bases make in water? Hydroxides, right? Arrhenius bases make hydroxides in water. Bronsted base is just something that can accept an H+. So tell me, ammonia, what's ammonia? No, so in ammonium has a 4 with it, ammonia. NH3, okay, so NH3, can it accept an H+?
Yeah, it can.
Yeah, what happens? So if I put a little H+ here, what's it become? Ammonium, and you know that's a thing, right? You can do that. So that's a Bronsted base. Can water, so water is amphoteric. We didn't actually mention that last week, but you guys wrote it down. Amphoteric is like ambidextrous, right, with both hands, right? So amphoteric means you can act as an acid or act as a base. So it's got both abilities. So what can water do with the addition of an H+? What does it become? What's that name? H2O plus, right? Because the plus that goes along with it. So it makes hydronium. Yes, that is hydronium. So that's it acting as an acid. Water can also act as a base. Okay, so if this is going to act as an Arrhenius acid, what's the definition of Arrhenius acid? Lindsay?
Arrhenius acid is it was not acid forms the hydronium in water.
Okay, so tell me how you could write this equation as it writes, or as it creates what you said in water.
So like how it creates the H3O.
Mm-hmm.
So we did like the way we set up with H and then the X. I like the example one we give H to X with H2O.
Okay, so you're supposed to write this one, how it acts in water. So I want you to take bicarbonate and make it act as an Arrhenius acid. So what should we add to this reactant?
H.
So we're seeing that it has to be, like how it reacts in water. We know it's going to be an Arrhenius one, so we have to put it in water. And then Lindsay, continue to tell me what you know it's going to make in water for sure, like as in the acid component. You can just tell me one part.
Oh,
H3. Hold on. If I'm an Arrhenius acid, what did you say it had to be produced in water?
hydronium.
Okay, we know a hydronium has to be produced, right? So straight off the bat, I'm going to write hydronium because the Arrhenius acids make hydroniums in water. I hope you guys are taking down a couple of these. These are really good examples to kind of recap last week's notes once again. So this has gained an H+, right? Where did it get it from?
H.
This guy. So this guy, bicarbonate, has taken this H and given it to water, so hydronium could come into existence, leaving what behind? CO3. So it looks like it's supposed to be a 1-, right? But hold on, you took another plus from it. 2-, so you dropped down one more. The charges are probably the harder component to this. So that's CO3 2 minus. Well, what's the name of this? Carbonate. That's carbonate. So a lot of times you're going to recognize what it is that's being made. So if you recognize, you're going to score, okay, like you've done something right. So this is acting like an Arrhenius acid. With water, hydronium is created. That is the definition of an Arrhenius acid. But sometimes it's harder to put it into action, right? So this is nice to have an example for how to make it look like it's donating H+, and then carbonate's being made. Okay, let's do one more. The conjugate blank for each of the following. So acids form conjugate bases. So what has to happen to this acid? It's going to be forming a conjugate base. H has to be removed, right? Because it's a bad acid. It's got to donate that H+. So it's a H+ donor. So this H has to be removed. So what does that become? So for 2 minus, right? Because that minus has to drop down once again because it's losing a plus charge. Yes. I'm actually, so the label here, I'm telling you these are acting as acids. So I'm telling you they're acting as acids. Remember, acids make conjugate bases, and bases make conjugate acids. You remember that from last week? I'll do another example with that shortly. Okay, so this one I'm telling you it's acting as an acid. So this is our definition of Bronsted acid. But I know why you're asking that. I'm saying it's Bronsted because we use the terminology conjugation or conjugate with Bronsted stuff, not Arrhenius stuff. Yeah, so if I'm ever saying conjugate, we're talking Bronsted stuff. Good point. Good point. Okay, so this one acting as a Bronsted acid is what? What's it make? We just remove that H, right? NO3 what? Minus. So if you don't put the charge, that would be a problem. Okay, that would be a problem. This next one? F minus, right? Because remember you're taking away an H+, so the neutral ones drop down to a negative charge. Now these are going to act as Bronsted bases, and remember they're Bronsted acids are acceptors of H+. So what is this one? HOH, and HOH is another way to write H2O, water. And that's just me adding an H+ here, and that cancels out that negative, a plus and a minus. So H2PO4, 1 minus, get it, now give it an H+, and what do you get? H3PO4, nothing, because that negative and that positive cancel each other out. And then this last one, HCl, and that negative and positive cancel each other out. So that's how you can go back and forth with your Bronsted definitions and so forth. All right, go see S3. Okay. So our next thing, let me go to our pH. So you can check yourself, possibly. These are the notes from Friday. We went over a couple examples, and then the computer froze, and we had a heart attack up here.
The guy kept talking.
And the guy kept talking. We were like,
What should we do?
I don't know. Okay, so, haha, here it is. So check yourself, and then we'll go over one of the ones where you go between H+ and H3O+, or OH- and H3O+.
Yeah. Wrong. Right, I thought I did them wrong.
Is
Yeah.
E supposed to be
I got
0.200?
Yeah,
it's not
5. Yeah.
For E.
It's supposed to be 0.2, and then I got 5.
Yeah.
So let me go over E.
Okay.
I got you. I'll go read.
And F was
Oh, were we supposed to? Okay, that's fine. I saw that, but I wasn't sure.
Only because this was counting my drops.
Okay. Okay.
All right, bring your attention over here. Let's look at this one. This is the very, very last one. If you've not done this, I would go ahead and start with me now. Okay, the answers on the board. The answers are meaningless without work though, so make sure you're with me. This is the last one, this is number 2, but it says the solution of ammonia has a pH of 11. What are the concentrations of hydronium and hydroxide? So in this case, I give you pH 11. Is it acidic or basic? Very basic, right? Closer to the 14 side is basic. So we already know this basic pH means I'm going to have more of which of these? OH. We know that this one's going to be lesser than this one. This is some conceptual stuff. You should be able to make some estimations without actually calculating. The beauty of logs, or if they're base 10, you can look at the exponent, and the exponent will tell you information about the concentrations, or about the pH, really, okay? So pH being negative log of the hydronium concentration means that if this is pH 11, what is the hydronium concentration? Does anyone know how to do that? So this is like, I forget how you write log in math, like base 10, x, something like that? Okay, so I don't know how to, you can't divide by log, you gotta do 10 to the negative log. But basically what happens is mathematically, this works out where your hydronium concentration is equal to 1 times 10 to the negative 11. Because that negative out front creates a negative exponent for your log function. So if the pH is a solid number, whole integer, the pH is the exponent associated with the concentration. So I can do that without a calculator. You're going to be expected to do a little bit by doing this assumption, which means I know that this is a really, 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 really high pH, meaning a really, really, really low amount of hydroniums, because those are acids, and this is a base. So you have 10 to the negative 11th hydronium. Now math, okay? What's the relationship? What's the equation that shows the relationship between hydronium and hydroxide? Not plus, right? OH, what?
Oh, times.
Yeah. So it's this one. Hydronium times hydroxide equals 1 times 10 to the negative 14. All right, here comes our exponent rules, right? So this being 1 times 10 to the negative 11th molar, this being x, say we're solving for hydroxide, is equal to 1 times 10 to the negative 14. What are you going to do? You're going to divide, right? So when you divide by 1 times 10 to the negative 11th, that cancels 1 times 10 to the negative 11th. What do you do with exponents when you divide them? You subtract them. So negative 14 minus a minus 11 is what? Negative 3, right? So that's going to be x, which is our hydroxide, is equal to 1, because 1 divided by 1 is 1, and then 10 divided by, or 10 to the negative 14 divided by, subtract, right? 10 to the negative 11 is 10 to the negative 3. Okay, so if this is the hydroxide concentration, what is the POH from this, using our functions? Not 1 times 10 to the negative 7. It's just, it's 3. The exponent is the POH, because the OH, when you take the negative log of 1 times 10 to the negative blank, the negatives cancel each other out, and the base 10, whatever causes the exponent to come down, and that's a 3. So this is the POH, but you knew that because you knew the pH was 11, so what does the pH have to equal? 14. So the pH plus POH has to be 14, meaning if I knew that, I already knew that off the bat, like there was no question about what pH was going to be. But I'm showing you how to use the exponent to go between the two, if you can. So in AP we try to do estimations, and this is one of the helpful tools. So don't forget pH plus POH is equal to 14, and that is equivalent to a similar expression, which is this one. So these two look eerily similar because they're referencing similar information, but these already have the negative log built into them, so it comes out to a whole number, versus these having their exponent, so it comes out to 10 to the negative 14th exponent. So they should correlate them. This is an addition, though. This is no multiplication. Oh, yeah. So someone asked me about the antilog. How do I get from, let's say, POH to, from OH concentration to POH? How do I get there? First off, tell me that formula. If I have the OH concentration, how do I get to POH? So if I have the hydroxide, and I'm finding the pOH. That one's the negative log one, right? So pOH is what you're finding. That's equal to the negative log of OH concentration. But what if I have pOH and I want to find hydroxide? That's the anti-log one, right? So you got to know what you have and what you can use, right? So in this one, if you have, what is the pOH? Okay, so you're solving for hydroxide concentration. That's our question of interest here. Then you'll do 10 to the negative pOH. This is the same thing as me saying anti-log of the negative pOH. This is generally what I'll put in my calculator, just 10 carat negative pOH. And you can do that way. Okay, so pH formulas, look at them, look at them, look at them. And then in terms of problem set 19, go ahead and look at problem set 19A. It's on the back of your notes. We have about an hour left, so we're going to do it for a lab. But look at problem set 19A. Tell me what you absolutely have no idea what to do. Those of you catching up from Friday are going to say more, but hold on. What have we not learned? Second, weak acids, you have notes on tomorrow. That'll be our last thing. So it's not bad. I got the pH calculation solutions on the bottom. So tomorrow I have to write curriculum for the county. Sorry. So I'll be out, but you guys have the majority of time just for work. There's like a weak acid video that's 12 minutes. You can speed up a little bit. You don't need to like Mickey Mouse me, right? Double speed is good. And the acid base much are the hydrolysis and reaction. If I can't do it today, I'll push it another day. But and then you'll be working on PS 19A. So you can do a little bit tonight. You can do a little bit tomorrow. Tomorrow we can also be working on your AP class. Okay, so I'll have the computers for you to do that as well. Okay? Yeah.
So when you ask for the concentration,
The number 3.
Yeah.
So that one says the hydroxide ion concentration. So you're looking for OH minus concentration, and oh no, I'm sorry. They give you the OH concentration right there, right? Further in number 3.
Yeah.
They give you the OH concentration. How do you find the hydronium from the OH?
Oh.
That's gonna be this equation here. Yeah, you got to know which one's hydronium, which is this one, and which one's hydroxide, which is this one. pOH is a form of pH, but pH measures hydrogen potential, like how much hydrogen you have. pOH measures how much hydroxide you have, but generally we don't always talk about pOH scale because it's actually opposite of the pH scale. So if you know the pH scale, we're in good shape. Because even if I give you pOH, convert that baby to pH, and then you're like, oh, it's a 5, it's an acid. Oh, it's an 8, it's a base. It's easy to remember like the generic definitions of one scale, not both of them. Because you can always convert back to pH. That feels easier. Yeah. No, I'm not sure yet. I don't have a date on it. Okay, let's talk about indicators really fast, and we're going to go back to our lab. Indicators. Who has ever in their life seen litmus paper? It's blue and it's red, and it changes opposite color. Boom. That's litmus paper. Write down a couple stuff, a piece of information for yourself. These two are the ones that we have to know for our end of course exam, and you have to remember which colors they turn. So, who can pronounce the second one? It's phenolphthalein. Phenolphthalein. I like to try. I like to see if you can. Like that dog. My name is Steven. Okay. So phenolphthalein is the one that turns pink. Phenol starts with a P. Pink is got a P in it, so I'm going to help you. I know that was a lot of help there. But phenolphthalein changes, it's an indicator, right? So if you need to indicate something to me, bless you, if you need to indicate something to me, it's going to be some visual. You're like, I need to know that. Or give me a really confused look. I don't know what we're talking about today. Or a really scared look, like I'm not ready for this AP exam tomorrow. So whatever's going on, there's a visual indicator usually that's going to help me realize what's going on. Well, in chemistry, these things we're working with are such a small atomic scale or molecular scale, they can't really indicate to us like, hey, I'm an acid, hello. They're going to do it in a different way. So we use other chemicals to help us see their properties so they can indicate something to us. And for example, we use pH indicators to guess what? Indicate their pH, right? So we've got indicators for different properties. So pH indicators generally will change color, and there'll be one color in an acid and one color in a base. So phenolphthalein is the one I'll start with because it's clear in an acid, so you can't tell. But once you allow it, if you know it's in there and it's still clear, this substance that we are dealing with is an acid. And if you put it in there and it turns pink, it's like a hot magenta, like Jasmine's shirt, really, really bright pink. And so it's going to generally be called a base. So that's going to be pH greater than 7. And this is a pH less than 7. So litmus paper, I used to have this jingle for it on blue to red acid, red to blue base. Okay, that was it. Okay, you feel inspired?
Yeah.
You guys think I'm something better. But blue to red acid, like it rhymes. Blue to red acid.
That's the last one.
Red to blue base. Look, you're gonna have to know this. Blue base, red acid. Red acid. I don't know. Acid. Base. So if you have blue litmus paper and it stays blue, is it an acid or a base? A base. If you have red litmus paper and it stays red, acid. If you have red litmus paper and it turns blue, base. Okay, you got it. All right, there's like a plethora of these. What's plethora mean? A lot. Okay. We've got methyl violet, thymal blue, bromophenol blue, methyl orange, bromocrystal green, methyl red, bromothymal blue. You've seen this one. Bromothymal blue. Did you use this in biology? It would turn green and blue? No? If you in my nobody had me for biology. Brandon. That's it. Okay. So thymal blue, phenolphthalein. So what you can see is that these different indicators change at different colors. So I generally say phenolphthalein is about in the middle, but it's not exactly in the middle. Where does it change color? Where is its end point? It's like a 9-ish. It's supposed to be a 9 right there. So it's clear on the 9 downside and pink on the 9 plus side. Which would be one that changes at pH 7? Bromothymal blue. So this one's one that changes about pH 7. So these indicators are used for different scenarios because it depends on where we have the pH changing. If it's changing, or if we think that something's going to have a pH of 2, well, heck, I might use methyl violet and see it changes at about 2. But if I put it over here with whatever this last one, if I put it with phenolphthalein, it would be very useless because it's not going to be turning purple or pink into pH of 9. So use these very specifically for whatever purpose you have, specifically for titrations. And we'll jump to those. There are some edible ones you may have seen in your cabinet or fridge. So curry powder changes from red at about 9 down to clear. Beets is a natural indicator. Apples, red cabbage is one we're going to use today. Tomatoes, peach skin, all of these things actually can change color because they have very similar molecular compounds on the inside of their skins that make them pigmented. And the pigmentation is actually what we're changing. So we're going to use the cabbage juice today. It smells like farts, people. Okay? So you're going to have to deal. It smells horrible. So what I would like for you to do are look at the 2 big lab stations in the middle. So in the very back, I have the nose, okay? So I'll be done in a second. The nose pH is 2 through 12. They have very pHs. They have very specific colors they change the cabbage juice. So those are the nodes. Those are going to be 1 brown color. So you put like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way through it. And then another person, unknown, these are the same on the left and the right hand side of the lab. And unknown is things like Tom's, shampoo, kitchen cleaner, lotion juice, Drano, blah, blah, blah. And so what you'll do is you're going to figure out the pH of those unknowns by looking at the color changes, not by using pH strips or pH tabs. You'll be using indicators to tell you the pH. So you have to make sure you know exactly which ones you put in which well, and then put the cabbage juice on top of it, or put the cabbage juice in first. But in the lab sheet, we'll be back here. I've talked down the volume, but they were overflowing, so try to get here as bad as you can. Okay? Don't mix up anything, or I will haunt you in your dreams. Okay? Please put goggles on. Maybe I already haunt you in your dreams, I don't know. 3 people to a lab group.
Um,